Good morning, everyone. Like a tryout, please, if you can listen to me, you can send me a message by the chat on the menu of the application, please. Good morning. Only for a tryout, please, if you can listen to me, please send me a message by the chat on the application menu. Good morning. Okay, perfect. So we will start. Good morning, everyone. My name is Hernán Ludovici. I am civil engineer. And today my goal is to talk about the composite structure concrete steel. During this presentation, the microphone of the audience will be muted. So if you want to share with us suggestions, comments, or ask questions, please use the chat on the menus application. And after the presentation, we will collect the question and all this information to answer or contact you by email. So for this presentation, we will work with this building. This will be our goal. We want to model this building that we can see on the screen or on the slide, and you can see two different parts of the building. working together, integrated, and we have a part of the basement with a foundation, different walls, and a slab in an underground level. And after that, we have also an structure on steel by the function of the roof on protection of the sun. So the tools to use during this presentation will have a CYPECAD and CYPE3D. CYPECAD is a program that in general target structures like buildings. We are talking with the word building with vertical supports like columns and walls, and horizontal elements like beams and slabs. In the case of CYPE3D, we have much more liberty of the geometry. We will work on this case for CYPE3D with bars, with elements on different angles on the space. So in this case, we have much more liberty, but on CYPECAD, in the case of work with buildings, we have a very, very interesting performance. We have also the possibility to design different kind of slabs, and we will show all these during the presentation. When we talk about composite structural elements or composite structures, we need to make difference between the composite structures and the composite structural elements. And same, we have in some cases the two possibilities working together in a same building. When we talk about composite structural elements, we have two images like examples. On the left, as you can see a column with the sole of a steel profile and encouraged by reinforced concrete. In the case of the image on the right, you can see a very classic composite slab. You have the part of steel-like form, and on the top, the reinforced concrete. Talking about composite structures, we understand the concept, talking on this case for buildings that have parts of reinforced concrete and some parts on steel. Maybe by the functional needs or maybe for architectural requirements, we mix these two kind of materials working together and sharing and make an effort of the better behavior of the two kind of structures elements. So our two structures for this presentation will have an space grid structure like that. You can see on the image. We will have an tetrahedron space grid. We can also see some columns, some supports, vertical supports, and some elements making the connection between the head of the columns and the principal structure on the mesh. The other part, the lower part of this building will be a foundation, basement, and first floor in reinforced concrete. We can see different elements composing this structure. We will have a mat slab, foundation beams. We will have some important columns, like features or different features for this structure. We will have a very heavy live load for the first floor. We will have a heavy traffic on this floor, and these 4 columns will be the support of the structure, the upper structure. We will have this section with the objective of securitize the possible accidental shocks or impacts. So let's begin. This will be our building and the final state of our project. I will focus this presentation on obtain this model. We will see at the end some results, but my principal goal is to show how to model this building on CYPECAD and CYPE 3D like an 3D integrated structure. You can see the mat slab, you can see also the beam foundations and the different elements that compose the upper structure. So we can start with the definition of the project. We define a new project with a name. We can accept. In this case, we will talk about an empty project. And we have here the different codes. Remember that we have a list of different codes. You can choose the code, the necessary code for the emplacement of the project. And we have the different materials, reinforced concrete, steel section for the steel, and the loads. We have the wind loading, seismic loading. We have some national codes and generic code and international codes. During the model of this building, I will use also the additional load cases. The combination are made automatically by the program, but the user can also define different load cases and use different categories for the live load. So now I will accept this menu, and on this case, for the definition of the position of the column, we can use different ways. We can define the position helping us with a DXF or DWG file. We can also use this virtual axis, but we can also define a grid with the tool introduction, grid lines, and now I will use the introduction of horizontal lines. For the name of the grid, I will use letters, and after that I will define 4 horizontal lines with a distance of 6 meters. I finished the horizontal lines, and now I will define the vertical lines. For the name, I will use numbers. 6 meters, like distance for the vertical lines. And making this work, I can also define for on the menu the layout origin point. This is very interesting in order to obtain after the manage and on the drawing the layout draw for like information for the implementation of the project on the reality. I can define the layout origin point uh, inside the geometry of the building or outside too. In this case, I will use 2.5 meters and 2.5 meters the distance between the origin point of the grid and the layout point. Now I can start with the definition of the columns. We need to define before that the height geometry. In this case, we will define two floors. The height of the second floor is only 1.2 meters. A live load and dead load of 0. Remember, this is the head of the support of the steel structure. For the first floor, I will define 3.15 meters of height and a live load. Remember, we will have a 1 ton per square meter of live load. And I will apply this load in two parts. The constant live load that we will apply in all the surface will be the 0.4 ton per square meter and a dead load of 0.2. We can accept and we can start with the definition of the columns. New column, and now we have some different features for the columns. On the case of a column have the initial point on a mat slab or a foundation beam, we need to define this column without external fixity. You, like user, have a help on the screen describing these characteristics, and you can share much more information on the screen to read all this help. So on the first column that we will use is reinforced concrete section of 60 by 60 centimeters. I will highlight that these are the kind of material that we can define for the columns. It's interesting to know that we can use reinforced concrete, steel, timber, and also composite beams. Remember the first image of our presentation will have this type of section. We can combine other kind of section. And on this case, we have the sole of a profile on steel and encouraged by reinforced concrete. Other case that we can define are a perimeter of steel and inside reinforced concrete. For our case, I will use reinforced concrete only. It's the kind of structure that we will define. So we need to, we can use, on this case, the grid. And clicking left, I will define the position of the columns. For the central columns, I will use two different sections. For the first floor will be the same, but for the second level, I will use a circular section of 50 centimeters. I can accept there, and I will position the central columns. So for this case, for the last column, I will change the fixed point. And now we can define also for the editing the floors, the elevation of foundation plane to define an underground, a basement. So the elevation of foundation plane, we will have 13 meters. We have our basement. I can accept there, and after that I can pass to the second sheet, beam definition, to see the state on a 3D view of our project. We have so the different columns and the central column with the support for the steel structure. After that, we on this sheet beam definition, we will work floor by floor. We can start with the foundation, and for this case, I need to define first of all the different walls. I will define a section of 30 centimeters, 15 centimeters at both sides of the axis of this wall. I can define for this wall the foundation, and in this case a foundation beam, where we can define the left overhang, right overhang, and the depth of this beam foundation. We will define 15 centimeters for every overhang, and for the depth we will use 60 centimeters or 0.60 meters. The beam foundation needs also the soil resistance and the subgrade modulus to define the reaction of the soil for the beam. Talking about an underground beam, we need to define, or we can define also the pressure diagrams. We can define this pressure diagram in different ways. For this case, I will use the definition from defining the soil characteristics, or the soil feature. And before that, I will go to the load cases. Loads, we can change load case as segment, loads, additional load cases, and we will define, on this case, for the soil pressures, new additional case. Soil, I will type a name, and I will change also, on this case, the necessary categories for the vehicles. We can accept and new. For our wall, I will go to the menu once again, and we have the 15 centimeters. We have from the foundation to the floor one, we have the foundation beam, 15 centimeters of section, and 0.60 meters for the depth of the foundation beam. The soil resistance, subgrade modulus, And now the pressure diagrams. For the pressure diagrams, we can see the load case of soil and the characteristics of different type of soils. In this case, we will use the low sun to define this pressure, and we need to define the up elevation. So in this case is 0. We can also define, for example, for this pressure with a water table. In this case, the up to elevation is the minus 1.5 meters. We can accept, and we need to apply this pressure on the left or on the right of the wall. You can see the pressure of the soil, and after the minus or 1.5 meters, the water table. It's added to the pressure of the soil. We can accept this, we can accept, and after that we need to define the position of the different walls and during the section of the basement. You can see the pressure of the soil outside the wall. So we have this geometry for our project until this moment. So we need to define to complete the foundation the different beams. And in this case, I will use the menu of the beams to define a foundation beam. We have different types. In this case, I will use the square or rectangular pattern. We need to define the width, for this case 70 centimeters, and a depth of 60 centimeters. We have the resistance of soil, subgrade modulus, as we have already defined for the beam of the wall, and we use the position of the different columns to define the initial point and the final point of our frames for the foundation beams. This is the state, and now we will define the slabs. The mat slabs that we can define on the panel manager. We have different kind of slabs, and the mat foundation with a depth of 40 centimeters, and the resistance of the soil and subgrade modulus, as we have already defined for the different foundation beams. Now we copy the panel and we have our basement. Okay, now we can pass to the second floor. On this case, I will use for these frames not a continuous section, but a variable, a combination of variable and constant beams. And this is more or less the type of section that I will use for our project. So to define this section, I will combine three type of sections: variable section, constant section, and variable section. And how we can do that? I can go to the first floor, sorry. I can go to the menu define beam. I will use, on this case, the drop beams, and we need to define a variable section, for example, with a width of 30 centimeters, the initial depth of 60, and the final depth of 40 centimeters. We can accept, and to define the length of this beam, I will use the tool coordinate introduction. On this menu, we have the delta x, delta y, and delta xy. So I will use delta x and delta y to define the exactly the length of this part of the beam. The initial point is the central point of the column, and I will use the delta x with an increment of 1.20 meters, and I have this part of the beam. The second one, it's the same, but with a negative value. And now I will use the delta y. Positive on this case, and negative for this one. This is the result of this introduction, and I will complete the beam with a constant section of beam. Now I will go to beams, define beam, a drop beam of 30 by 40 centimeters. I can accept. And I will complete the section. Now I will copy this beam to complete the different frames in X and in Y. So to do that, I will go to groups, copy elements of the group, copy elements in the same group, and I will copy beams. We need to select the three elements, the three components, and I need to copy with reference to the central point of the columns. Now the same, but this time for the Y direction. We finish the copy and we can see the result of all this. Now we can define the slabs. For the slabs, I will go to the panel, define panel, and we have different kind of slabs. Remember, we have, for example, the composite slabs. We have already thought about this kind of slabs. It's a composite element, a structural element, and we have the form deck and composite deck. The user can define his own library depending on the supplier. For our project, I will use a flat slab of 20 centimeters, and we need to click on the close perimeter, and after that click on a wall or a beam to define the direction of the reinforced bars. After that, we can copy panel and everywhere. So remember that we need to define an stairs, like communication, a way communication between the the basement on the underground slab and the first floor. Okay, so to do that, I will use, I need to go to the floor one, the initial point of the staircase, and I will use the modulus stairs. In this case, we need to define an span, one span with different forms. We can use in this case, for example, the library, and using, starting with an element from the library, I can edit this element to adapt to our project. We can see that the change in the level is 2.80 meters. Remember that we have 3.15 meters to change in the level. So I will adapt some of these parameters for my project. So in this case, I will use 7, and we have now the change in level of necessary change in level. I can accept there, I can accept there, I can accept, and now I need to define the position first at all the direction of the staircase, and we can move the staircase with different point of reference. And we have on the first floor the slab, so we need to define the space to the staircase. To do that, I will go to the definition of the beams. The support beam will have a 30 by 40 centimeters of section. And to limit this slab, I can do that with a beam, or for example, with a limit beam. This will be the space for the staircase, and now I can see the space defined. So the model is finished. We need to define the live load that that will be complete the 1 ton per square meter. Remember that we have on loads and groups, and we have only for the 400 kilograms per square meter, and we need 600 more. To do that, I will apply the alternance load. We can do that going to the load, the loads in groups, and we can define on project general data and additional load cases, and I will define one load case with 2 different positions. Will be compatible and we can accept. We can see the combination defined automatically by the program. This will be the combination that will be applied for these different loads. And we will go to the surface load on slabs to define the 0.6 ton per square meter on a load case of live load 1, position 1. We can add and we can select the different slabs where the load will be applied. For the second disposition, I will add these loads to the other perimeters. The case is to obtain the worst situation to ensure the security of our structure. That will be shown at the end on the result of this analysis. So now we have the lower part of our structure, and I will define the model of the steel structure. To do that, I will use the modulus 3D structure, integrated 3D structures. We need to define, first of all, the point of support, and this connection will be validated clicking right and validate connections. Validating these connections, the workspace of CYPE 3D appears, and we can start with the definition of the 3D integrated structure. Now I will go to bar, new, and on this case I will use the cold form steel. We have some libraries. I will use the 5 by 15 section. I can accept, and I will define the supports with a height of 5 meters. Sorry, I will go to delete, and we can new 5 meters. Okay, now I have the necessary 5 meters of 8, and we can see that different plans and different line of reference are automatically created by the program to help me to define different levels. In this case, I have the 4 supports, and we can define now 2 bars that will be the base of the generation of the structure and tetraedrons. I will go to the definition of the bars, and now the section will be different. In this case, the 3 by 276. I used the different nodes to create these 2 bars, and to define the tetraedron mesh, I will use a tool integrated on the program that is called generation. We have 3 kinds of generation: plans, nodes and bars, and tetraedron mesh. I will use the tetraedron mesh. I need to define, first of all, the origin of the generation, the first direction, clicking on the second point, and after that the third point for define the second generation. Now I can see on the menu different parameters that the user needs to define. I will divide this one direction in 6 different bars and the segment 2 in 6 also. And the distance between the planes will have 1 meter. I can accept, and now I will define for the created bars the kind of section that is necessary. I can select all the bars, clicking right, I will have the 3 diameter profile. And now we can see the state of our structure with a 3D view. We can extend this structure on both sides, and that will be my goal now. To do that, I will use these menus, and we can also use the tool copy elements. I can select the groups of bars that we need. Clicking right, I finish the selection. I select the initial point and the final point for the copy. And now I need to repeat with Control C, Control C. I will select the bars, selecting the initial point and the final point for the copy. And now for the other side. Same, Control C. I can select the necessary bars, Control C, repeat the action, and now I will go to 3D view to see the state of our structure now. Okay, the dimension of the mesh is the necessary, so I will define the support and the connection. I will edit the connection of the supports with the structure. I will define other type of connection. To do that, it's just a little complicated to work like that with a very important number of bars and on 3D. To do in an easy form this this addition, I will use on the program the tool Open New. I will define a new window from a 3D view of a selection of elements, and I will select some elements to define this 3D view. I will name auxiliary to this window, and this is the result of this new window. It's only a view, and the activate window contain all this. So I will define the connection of the column with the structure. To do that, I will define some elements. On this case, the section will be different. I will use a 4 for the diameter of the profile. I can define the initial node of this bar in reference with the initial or the final point of the column. I fix the distance in 2 meters, and after that, I define the 4 different bars for the connection. And now I can go to bars and delete the part of the column that we don't need. Now I can go to the 3D view, the activate window, and see the result of the addition. I need to complete, on this case, some triangles, some bars to fix and ensure the non-deformation or triangular structure. I will define new bars, and I need to go to generate nodes at the intersection points to define the middle point of this. So if I go to the complete structure, we can see that for this column, the support is different, and I need to define this support for the others columns. I can see I can do that repeating the action or only copying. I will save time with that. So I will go to the menu window. I will use the vertical tile, and I will use some of the tools of the program in order to save this time. For that, I will go to show and hide planes. I go hide planes, and now these are the different columns that we don't need for this structure. So I will delete these 3 ones, and I will have the selection on this window that is much more easy. So I will go Control C. I will select the necessary bars. I finish the selection. I take this point, the base of the column, like initial point, and I pass to the other window to copy to the other's base. So now I can see a 3D view. Now we have the complete geometry that we need. Remember that the self-weight of the bars are taken into account by the program. But if we need, for example, define some loads for the structure, we can, for example, go to load and introduce, for example, loads on node. I will select all the nodes of the top surface, and for this case is very light, but I will define, for example, 50 kilograms in the direction set. We can accept, and we can go to the visible load case. We can see all the different loads, and it's very, very little, but we can also, for example, go to the scales, and we can define for the deep load and a scale of 20, and like that we can see much more easily the loads defined for the nodes on the top level. It's only for an example. Maybe in the reality we need to have different loads on the perimeter that on the middle, but remember that is only an example. My principal goal is to show how to model the structure. So I can go to the workspace of CYPECAD, and we have our model. Now I can launch the analysis and the design. So to save the time, I will try to show you some of the results that are very interesting to show. For example, in order to obtain, for example, the results, we can go to the sheet results, and it's very, very interesting always to check the deformed shape. We can, for example, add the waffle and the slabs. This is the mesh for the discretization. Remember that we have the alternative loads that it's interesting. For example, for the live load, I will show, for example, with a deformed shape more and bigger factor. We can see the live load, the load case of live load on all the surface. And remember that we have two other disposition of load, and the second one, or the third, is this one. So remember, the program will combine these load cases to ensure with the envelope the worst situation for the different position of the loads. This is very interesting in the case of to have a very heavy live loads. Other interesting results can be also, for example, the contour maps. We have different, for example, live load, or in this case, for example, for the second one, we have the possibility to see the deflections and control the deflection with this tool. We have also the possibility to see the integrated forces on this strip of 1 meter, for example, and we can see, for example, the total shear, or we can also see, for example, the flexural moment, and we can integrate these forces of the slabs on 1 meter of a strip. This is very interesting to check the result of the program. Other interesting results can be, for example, the beams. We have the beams with a reaction from the soil. Remember that we have showed the foundation beams. This is the type of diagram, and in the case of the beams for the different sections, we have these reinforced bars. We can edit all that. We can also obtain some checks, all the checks that the program control for the element is are there, and we can obtain the reports. We can also do that for the columns, for example. We can see a 3D view for the column. For example, this is interesting because the change of section is not very common, and the program will solve this change of section. We can also obtain the detailing. We can have all these on drawings. And talking about the drawings or layout, we can also obtain, for example, some of the drawings of the project. I will check only or show some different drawings. We have much more type of drawings to obtain from this project, but it's only for instance. Remember that we have the staircase. It's very interesting to have the design of the staircase with all this information obtained for the drawings. That can be a very, very interesting save of time. We can also obtain the layout of the different columns with the point of layout and the grid lines. And we can also see, for example, some of the frames. You can see that the bars have reference with the position and with the reaction of the soil. And this is the variable section combined with constant section on the middle of the frame. So this is more or less the presentation. The goal of this presentation will show different possibilities, different ways to model a program, and some of the tools of the different programs that we have, CYPECAD and Sci3D. Thanks for your attention and welcome to the family of CYPE.